Okay, I will now invite Thomas Kaiser and Thomas Loeffler from Denso to give us a presentation about the interaction of cathodic protection with coatings on pipeline systems.
Yes.
Welcome to Thomas and the other Thomas.
Yes.
So you're combining both Thomas.
Yeah, double
well
Thomas.
Done.
Yeah. Okay, thank you for the nice introduction. Also a warm welcome, ladies and gentlemen, from my side to the audience here and also in the web. I have a talk about a topic that came up more and more the last years, decades, and just for me, we guess there's this, a lot of misunderstanding and often a misuse of the wording, and I try to give some facts and to more details according to this topic. We are talking about coatings, and coatings have to suffer a lot of various impacts. It's chemical, it's physically, and of course different impacts during the lifetime of the coating, during application, during transport, during installation, and of course during operation. So this is just an overview. And what is the task of the coating? The task of the coating is to keep the corrosive elements away from the pipe at all times. And the corrosive elements, these are in the soil, usually oxygen and water. So what is the coating doing? The elements are diffusing around, and the coating prevents these corrosive aggressive elements to reach the steel surface. So therefore the coating is the first line of this defense, one could say. Additionally, cathodic protection is installed. This is the second line of defense. According to our opinion, this will only be needed and act in the case the coating is damaged. So how does it work like? We have a defect shown here. And the cathodic protection power supply will supply sufficient electrons to these defects, such that there will be no corrosion occurring at the defected area. You can see here the electrons are going and the coating defect is protected. Looking more in detail, what's going on here at the surface. We have now a defect in the coating. So such means that the corrosive medium can directly get into contact with the steel. So again, we have the oxygen, the hydrogen going around, and to some kind there will be a surface reaction of the species. Actually, we're looking at a case that there's no cathodic protection. The electrons of the steel, of the ions, are transferred to the oxygen. This is a typical electrochemical reaction and forming an iron cation. So iron gets dissolved and we have alkaline. The species diffuse away and the dissolved iron then leads a defect into the steel. So you have corrosion. And that's what we don't want to have. So what is this cathodic protection then doing? So cathodic protection gives you a quantity of electrons that can be used or that react with the oxygen of the soil, such that the electrons are not given by the iron, so the iron is protected, and therefore you have no corrosion. Of course, also in this reaction you have alkaline being formed. In this region where there's a direct contact of the bare steel with the soil and the activated cathodic protection, you have a no corrosion reasoned by the activation polarization. But furthermore, being by the alkaline formed, you have a concentration gradient of pH. This is based on the chemical, electrochemical reactions. So, even in the case that you have a disbonded coating areas, like this, near the defect, the pH level increases by the diffusion processes to an alkaline level that protects these areas. This can be clearly seen by the Pourbet diagram, which is published since decades of years. And this we call the concentration polarization protection. So it's an increase of pH. There's no direct access of the electrons, but you have, due to the increase of pH, you have a concentration polarization and protection of the steel surface. So, of course, there are some factors that might influence the flow of the cathodic protection, such as metallic structures in the past, interferences from nearby structures, or shorted casings. I think all the people who are familiar with the corrosion protection know about this. But, of course, one of the most influent factors are high resistance of the soils, non-conducting materials such as rocky terrains or dry grounds. So now, coming back to the initial text of my talk, what about the discussion about shielding coatings or non-shielding coatings? How did it start at all? So in the 60s, or till the 60s, there was often used bitumen-based coatings on the pipelines in Europe. And then with the time of the 70s, one decided to use newer, modern materials based on plastics, on polyolefins like polyethylene carrier foil or PVC carrier foil with an adhesive based on batyr rubber or even also a bitumen rubber adhesive. So this was the first step of development, of improvement compared to the pure bitumen, because bitumen was well known to brittle with the time, to lose its properties with the time. So after a decade, it's not in a good mood anymore. So what happens when you have a tape based on these two-ply systems? You have microtunnels remain during the wrapped area, because the carrier foil and the adhesive layer do not form a hose-like coating, because they are not able to amalgamate. So when looking at the in detail at this model, then you can see that in the contact area of the adhesive to the plastic, to the carrier layer, so oxygen and of course also water can diffuse in here and get in contact to this direct steel, therefore forming an corrosion. This is the result. In the case of deep two-ply tapes, for instance, so you have a mechanical loading, you can imagine by indention during the lifetime in the buried situation. So you have water and oxygen entered at the defect, and now you have the CP that works at the second line of defense, and there will be no corrosion near the defect, as I showed you. Looking more in detail and some more distance. So at the first glance, we have a good protection, but there are still microtunnels in the overlapping area of the two-ply tapes, which I showed you. And they enable water and oxygen to access from the defect area. They fill it up, and they will lead to progressive disbondment. And the channel is formed following the spiral overlap. So the oxygen can diffuse into the through this weak area, reaching the steel surface and forming a corrosion. And this is a spiral corrosion. And this has been observed shortly after the two-ply systems have been put into the market.
Is this the cathodic shielding or?
I come. So is now the next phase, yeah. So the question is, why does the CP in this case does not protect against the corrosion? It's protecting here near the region, but it does not, cannot follow the whole spiral, and therefore there is no activation polarization along the spiral. There's also no current that can flow through the overlapping area. But the molecules, as I showed again, the molecules can diffuse and reach the steel on wet surfaces. So therefore, two just bonded tapes allow a diffusion of the molecules, of the aggressive molecules, but at the same time, they provide an electrical shielding, as the electrons cannot follow. And this, from the cathodic point of view, this is a shielding effect. So knowing about this, there have been two different approaches being developed. So one is to continue with the two-ply tape technology, but allow the water and the oxygen to get in contact with the steel surface to transport the current from the cathodic protection directly to the steel. Therefore, the current is strictly mandatory to flow at any time and any place. The option B could be to provide a hose-like coating which have no microtunnels. You not allow water and oxygen to get in direct contact with the steel surface. You have the current of the cathodic protection as an additional protection, the second line of defense. Coming to option A. One option is going around in the field is a polymeric mesh back coating. It's a woven geotextile fabric backing on a rubberized bitumen. So it's always as wet as the soil. You have only one layer of corrosion protection system. It's the rubberized bitumen. This keeps the corrosive media away from the steel. So we are continuing with the two-ply technology to solve the problem. This means the idea is eliminating the shielding effect, which I explained to you, of a two-ply system by providing excess of the current, of the cathodic protection current, at any time and any place by using electroconductive and water-permeable material as a carrier foil. It's like this. Now, the electrons can flow and prevent the corrosion. So theoretically, you have no corrosion. Again, the situation. Here, with the time when the water goes in, with the time you have, we will have despondment. But the water is brought with the steel, this is the despondment. But now the electrons can flow through this layer and the cathodic protection works. Remember, an insufficient adhesion of the two-ply tapes resulted in the penetration of water and caused the spiral corrosion. By providing only one protection layer that keeps the corrosive media away from the steel situation with polymeric mesh back coatings is getting even worse. The argument against the fear using a geotextile fabric is gained conductivity, as I showed you. But is this really an advantage? Well, as you can see, the electrons can flow, but is it really an advantage? Let's look at the cathodic protection criteria one should have taken into account. And what are these? For simplification, we can go on. That's a cathodic protection current, as everybody learned at school. Current is direct proportional to the cross-section area, and it's inverse proportional to the specific resistance of the materials, and of course, the length of the pore. Now, coming to a situation, we have a high soil resistivity. It's a dry period. The water in the ground removes, and with the time, also you only have a small reservoir within these small pore. What happens? The decrease of the CP current occurs because of the resistivity increases, and you have no sufficient cathodic protection anymore. The corrosion starts. Now you have a raining period. The reservoir of the soil is filled up with water. You have conductivity again. Electrons can flow. The increase of the CP current can be observed. Corrosion stops. But it's not always all the time wet. You know, in reality, with the time, again, you have a dry period. It dries out the whole soil. Also, the geotextile fabric will lose conductivity. For the current, the decrease of the CP current will occur. The species oxygen will still diffuse because they are in the ground. And you will have, with the remaining humidity, you have continuous corrosion. So the despondent area is frequently filled with fresh water and oxygen. The soil and later the pores dry out, but not, of course, the whole despondent area.
So in other words, you will have to be watering the pipeline.
This would be an option, yeah? That's a good idea, yeah? Or you can remove the oxygen from the environment, then you have no corrosion. But I don't think that it's so helpful for us, for fauna and flora, yeah? Okay. So another criterion is the dimension of the pore. So we have a buried pipeline. What is with the buried pipeline? We had some talks about the pressure coming on. So we have a soil pressure, and this, of course, could and should remove. It's expected to decrease the pore dimensions. So if the pore dimensions decrease, the cross-section area, then you have the decrease of the CP current, and this results in corrosion. Again, corrosion. Now, we can think about a worst-case scenario, but it's realistic. Yeah? We have a buried pipeline, we have changing conditions in the soil. I'm not talking about days or months. I'm talking about years and decades. So in this case, yeah, we have a high soil resistivity, changing conditions, and we have a soil pressure, then the CP current is at a minimum and corrosion at a maximum. So what is most likely are the realistic conditions in the field? Is it we have no changing condition, only wet soil, as you mentioned? Do we have no mechanical pressure on the coating? And we have always perfectly working cathodic protection at any time and place? Is it realistic? Or do we have changing conditions? So it's a dry period or wet period. Do we have a mechanical pressure on the coating? And cathodic protection is in place and ready for working stable. So, therefore, we think that this option A does not seem to be a good solution. So option A for reminder, it's to continue with the two-ply technology. We allow the water and oxygen, the aggressive media. We allow these media to get in direct contact with the steel surface, and we strictly mandatory, neatly, the current flow at any time and place. So what is it about option B? We provide a hose-like coating, no microtunnels. We allow the water and oxygen not to get in contact. We prevent to get these species to get in contact with the steel. And the current is a second line of defense, the current from the CP. So what about this option? For example, it could be, but I will show you later, there are other possibilities. It could be a three-ply tape system, so a hose-like coating. The idea is that we have an adhesive layer of a butyl rubber on outside and on the inside of the tape. Therefore, we can form a water and oxygen-proof hose. We have no despondment of the layers, and therefore no spirally channels formed. No corrosion, not even a distance of the defect, because the defect area itself is protected by the cathodic protection. How to explain it? How you how does it work? So we have a three-ply system. We have a high-grade polyethylene carrier foil on both sides. We have a butyl rubber adhesive. When they're wrapped around, these butyl rubber adhesive layers get into contact, and by an intermolecular diffusion of the mobile molecules, we have a homogeneous layer which you cannot distinguish anymore. And this you can see in the photo here. By the self-amalgamation, you have no difference in these two layers. These fused layers, outer and inner butyl rubber adhesive, form a water and oxygen-proof protective hose. What are now the properties? We have no spiral channel formed of the properties of the butyl rubber adhesive. We have not water and oxygen getting into contact with the steel surface. We have no despondence, this is because of the properties. We are independent on what's going on outside. It's completely independent. We are independent on changing on mechanical pressure as long as there's not a defect occurring. If there's a defect, we have the cathodic protection for working. So, therefore, the cathodic protection is not mandatory, only in the case there's by an impact and defect, no corrosion. Even in an unlikely event of disbandment of a hose-like coating like this, the mechanism of inhibition through the pH level protects the pipeline, as I showed you. Within CP working, we have a concentration gradient of pH which goes underneath the coating and protects the steel. That's a fact. So we have no corrosion due to the activation polarization, and we have no corrosion due to the concentration polarization. If the CP is interrupted for a while, you still have, for the whole time, as long as the pH is in a right value, you still have a protection of the pipe metal through the concentration polarization. So let's compare again the two options I showed you. The one is a non-shielding tape based on a 2-ply polymeric mesh back coating. Or we have a hose-like coating, for example, a 3-ply tape, high-grade co-extruded and a self-amalgamating. We have the situation I showed you. We have a low soil resistivity, no soil pressure, and a constant high soil moisture. That's what Johan recommended. And here we can say the spiral channels are filled with water. The mesh is conductive. CP works, no corrosion. The same with the hose-like coating, independent of what is outside, as long as there is no defect, no channels, CP is armed, no corrosion. Coming to another thing, we have a low soil resistivity, no soil pressure, but now, realistic, we have a changing soil moisture. I showed you this results in an insufficient cathodic protection, and there will be corrosion. The same in the case of the other system, the hose-like coating. It doesn't matter what is outside occurring. It's still protecting the pipeline from getting in contact with oxygen. We have a third case, low soil resistivity, but now we have the soil pressure, reducing the pore diameter and decreasing the cathodic protection current. You have a corrosion in this case. Again, as long as there is no defect, the remaining or the materials prevent oxygen to reach the steel. If there is a defect, then we have the cathodic protection. So cathodic protection is armed, so no corrosion. And now coming to the worst case scenario, I told you, this results in a minimum CP, in this case of coatings, and a maximum corrosion. In the case of a hose-like coating, we have no channels, CP is armed, no corrosion. Coming to the conclusion, applying a polymeric mesh back coating, the type A variant I called you, the so-called non-shielding tapes, to avoid spiral corrosion by supporting the current of cathodic protection to reach any area of the pipe, is first of all a very questionable approach. Because do you think it's a good solution? We provide only one protective layer. We enable the water and oxygen, the aggressive corrosive media, to reach the steel surface. We assume, one has to assume that there are no conditions changing with the humidity of the soil and therefore the conductivity. And we assume there's no pressure reducing the pore diameters. And we always rely on the perfectly working cathodic protection 24 hours a day, 7 days a week, all the year. Furthermore, I mentioned at the beginning, using old-fashioned bitumen-based adhesive, this can fail only because of the weakness of the material bitumen. When aging, bitumen gets brittle, and it's clear, and does not provide any reliable protection anymore. That's the fact why in the 60s the bitumen was substituted step by step. And now we're coming back to this old-fashioned technology. Okay. So why should you weaken the first line of defense, the coating? Finally, any coating, factory coating or field-applied coating, should always be designed to perfectly protect the pipeline. In the case of the field-applied coating, hose-like coating, such as the liquid coatings, the shrinkable sleeves, and the mentioned self-amalgamating three-ply tapes, provide, according to our assumption, the best solution. Because they're preventing water and oxygen to reach the surface. They work under each conditions outside, wet, dry, it doesn't matter. And they enter pressure on the coating. And if they do not enter the pressure, I have to repeat it, then we have the second line of defense which protects the bare steel getting in contact. Cathodic protection serves as a second line of defense. Therefore, choosing a corrosion prevention system that works under any condition, this is the first choice. Shielding or non-shielding, this is not the real question. Non-shielding products, such as polymeric mesh back tapes, are based on an old-fashioned technology, which proved to fail in fields, as I showed you, the two-ply tapes for corrosion prevention. By promoting the non-shielding effect, the huge disadvantages of those polymeric mesh back two-ply tapes are somewhat compensated. But this takes place, as I showed you, at the expense of other important properties which are then significantly weakened. And I hope, now I'm at the end of the talk, that you understand that the best solutions are modern, high-quality hose-like coatings, and they usually have shielding properties. And at the end, there's a light, and I hope I bring the light to you. Thank you very much.
Any questions? There we have a question.
Thomas, can you go back to the slide when you make the comparison between the two coating systems? There was a big... this one.
Okay,
yeah.
just.
Yeah, you can put all the everything. Yes. So on the non-shielding tapes of the shotgun column, the center column, why do you assume that those coating system will fail, will disbond, while you assume that the three-ply coating system will never fail or disbond?
The thing is, I have to go back somewhere else.
Okay, Thomas, I know, but
we have to look at the okay, we can go here because you have water and oxygen, water brought.
This is not my question.
Okay, I want to explain you why it's despondent. Because you bring water to the steel surface, and water despondence with the time. I'm not talking about days. I'm talking about years and decades. And this path of water is not available for the three-ply tapes, for example, because you have, I showed you, you have this inter-amalgamation process. And that's the answer of the question.
You cannot,
I can go back, yeah?
Yeah, can go back to the table. You cannot compare two coating systems pretending that one coating will never fail. All coating can fail. If you assume that your coating on the right column will never fail, then, and if I assume that the coating in the center of your table will never fail as well, then you have the same conclusion. So all the question is what happened if a coating failed. I agree to say that the three-ply tape has less probability to fail. That's true. But if it fails, what happened? And this is not explained in this presentation.
The failure you are talking about is a despondment. And the despondment is increased by the transport of water to the boundary. And this is only in the case of the two-ply systems, because you have a path of water reaching the surface. If you have a hose-like coating, water cannot reach the surface, and therefore you have, per principle, you have no despondment. So that cannot occur.
This is one failure possibility, but there are many others possibilities or many other factors which are conducting a coating to fail. So considering that a coating never fail, of course it never corrode. But the point is, yes, a coating can fail. And what happens if it fails?
Then is the question, if a coating fails, then is there a path of water and oxygen reaching the surface? In the coating on the right side, there is never a path of a coating, except you have a defect, a mechanical defect, and then you have the cathodic protection as a second line of defense.
No, you can have
these are also, and these are also circumstances.
You can have a bad application. You can.
You can always have.
There
a
are
bad
many factors. Yeah. While field-applied coatings are failing.
That's right, yeah.
Yeah. So what happens if it fails?
Any other question?
Oh, if it fails, yeah, then you mean it's...
Sorry, we need to have a microphone.
If you say that it fails, then you means it is disbonded from the steel, but it's still a close hose, and water and oxygen does not reach the steel. That's the difference. It will reach with a two-ply tape because there's diffusion. Two-ply tapes are only bonded. Yeah, they are not amalgate, and that's the difference. No.
You're right, there is a diffusion, and this was calculated by Professor Schwenk in the 70s, according to the three-ply systems that came into the field in Germany, and they calculated a corrosion rate from the diffusion of oxygen through the layers of the polyethylene, through the layer of butyrubber you can read in the literature, and you have a range of 0.1 micrometer per year. So this is a theoretically corrosion rate by the diffusion through a hose. Or maybe it's 1 micrometer per year. I don't know about it, yeah. But it's for 100-year life expectancy of a pipeline, it's negligible.
From what I can hear, it seems that they're all working on this shielding effect that is creating the problem, and then you're trying to limit as much as possible by different technologies. But as you say, perhaps you cannot eliminate completely. So it's, this table is an indication of the, I would say, higher probabilities that you can have better control other than, but as you say, nothing is 100% as certainty. Basically is what is being discussed. But you will have in the coaching group the possibility to discuss further this.
Yes.
So, any other question? So, thanks Thomas and Thomas.
Yes.